Hello everyone, my name is Ryan Lott. I'm with the Arkansas Signal Integrity Community, and today we're going to be talking about mode conversion, or more specifically, differential to common mode conversion in differential interconnects, otherwise known as SCD21. So before we begin this lecture, I'm going to basically set the prerequisites. I'm going to assume that you understand what a differential channel is. So we're talking about differential interconnects. And if you don't know what those are, you can feel free to ask me any questions that you have. And also S parameters, and more specifically, mixed mode S parameters. If you don't know anything about these, I would definitely recommend going onto a website such as keysite.com. They have tons of white papers on this. Basically, I'll do a quick small review. You have a 4-port microwave device, or let's say a high-speed device, and we have 4 ports. And you can almost imagine as though you were sending in some sort of digital pulse from line 1 to 2 intentionally, and the exact same pulse except opposite polarity from 3 to 4. Now, why do we do this? Very quickly, this is the whole point of differential interconnects. When we have 2 transmission lines working together as one, where one channel is sending a data pattern, and the other is sending the exact same data pattern except in opposite phase, through the process of subtracting these two, we get a very nice and clean channel. And when I mean clean, I mean it's less susceptible to noise, return path discontinuities. It has its own physical properties, and I definitely recommend taking the time to do the outside research and actually understanding these types of channels for your own benefit. And basically what I'm getting at is that even though this is what is intended, there still is sometimes a little what we call a common component that gets added into this equation. So again, things are expected to be equal and opposite in a differential channel. However, this is never the case. There's always a little bit of phase difference between the 2 channels, and there's always going to be a little bit, there's always going to be at least a little bit of difference in their amplitude. So they're not exactly opposite, and they're not exactly equal. So that's just a quick rundown for the people who have never heard of this. But like I said, this is mostly for the people who have. So let's go back, and as I said, we're going to be focusing on SCD21. So for those of you who know, SCD21 is basically equal to S21. By the way, I'm going to be using the 1 to 2, 3 to 4 format. SCD21 is equal to S21 minus S43 plus S41 minus S23. Remember, these are phasors, so they have a magnitude and phase. All the components divided by 2. So what exactly is that? This is a function of omega, and all of these here are also a function of omega, or frequency, whichever you decide to use. So what exactly is SCD21? Like I said, we're doing differential channels here, and we're assuming that if we are focusing strictly on phasors and sine waves, that one channel is, if we could focus on one frequency, is sitting in frequency with a specific amplitude A, a certain omega, and let's just say for right now it has some phase, and the counterpart is exactly opposite. And we'll say that he has a magnitude B, the same omega, I guess we'll call it omega naught, and his own phase. And if we were to subtract these, we would get a really nice big sine wave, twice the amplitude. And if we were to add them, we would get nothing. But of course, there's always going to be some situations where the phase of A is not equal to the phase of B with respect to 0, And so we may get differential component that might be 95% of the original 100% value. But when we add these, we get a very, 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 very small 5% common component. And this 5% common component right here can lead to very disastrous results if it's not controlled in a reasonable manner. It can radiate if it's in the right environment. It can bounce around and cause all kinds of intersymbol interference problems if it's converting back and forth between common and differential, and many other things. So that was, I guess, again, a second primer on this. So, like I said, we're talking about waves at a specific frequency, and here above we have our formula. And mode conversion is nothing more than these phasors being at the very wrong settings. I'm sorry, I'm stumbling over myself. It's a little bit tricky to understand. So I guess the best way to go about this is to draw a phasor plot. Draw a formula one more time. S21 minus S23 plus S41 minus S43 all divided by 2. So you can imagine you have one S parameter, that's S21, another that's S23, another that is S41, and then another one that is S43. Now they don't look like this in real life when you make actual measurements, but let's just assume this case. And they all have their own angles. Let's call them theta A, theta B, theta C. I know this is getting a little crowded, I'm sorry. And theta D. And they all have their own component values. Okay. This is just a reminder of phasor notation. I expect everyone to know this. Now let's do a little trick. We have this 4-port device, and we're intending us to be shooting a differential signal into the differential port 1, and we're intending all of it to come out on port 2. Now let's ask the question, for mode conversion analysis, what is the best way to kind of understand exactly what creates this common component? In my opinion, the best thing to think about is that imagine you're shooting in a differential signal into differential port 1, and you're looking at the individual single-ended outputs, otherwise known as SCD21 and SCD41. Like I said, we're shooting a differential input into port 1 differentially, and we're seeing how much we're getting out on port 2 and port 4. So let's rewrite our formulas here a little bit. I'll do it again one more time. Sorry. Sorry. Okay, great. There's a million ways you can write it, so now let's group these. Let's say that SSD21 is equal to S21 minus S23 divided by 2. And we'll say that SSD41 is equal to S43 minus S41 divided by 2. So now if we were to draw our phasor plot again, this could be SSD21, this could be SSD41. It's angle B, we'll say. It's magnitude B. This one's angle A, and it's magnitude A. So if we were to rewrite our SCD21 equation, we would now see that SCD21 is basically SSD21 minus SSD21. Now, why is this important? We'll see that in a second. So as I said, SSD has a magnitude of A, an angle of A, or SSD21 has a magnitude of A and an angle of A, and SSD41 has a magnitude of B and an angle of B. So we can write this in phasor notation. Say that A e to the J alpha, or not alpha, theta A minus B e to the J theta B. These are just the phasors that we wrote here. So now let's apply another trick. For mode conversion, we really don't care about their absolute angles. We really just care about the angle relative to one another. So let's again redraw our phasor plot. Now let's pretend that this first SSD21 phasor is completely real. There's no imaginary part. And that SSD41 has an imaginary and real part. So now we can say that the angle between them is theta AB. SSD41 has its magnitude component of B, and SSD21 has its magnitude component of A. So now, once again, we can rewrite SCD21 as a simple formula of A minus B e to the J theta AB. So now we have simplified our analysis of SCD21. We went from a 4-variable formula right here down to a 2-variable formula where we only have one phase factor and 2 magnitude components. And again, these are functions of frequency. All these formulas apply to a specific frequency across an entire band. So now we're going to get into the good stuff. We care about, most of the time when we're measuring high-speed differential devices, whether it's Ethernet or PCIe or what's another one, HDMI, or just, for that matter, any high-speed channel. All this matters. SCD21. How high is it? So a lot of times, when you're measuring things such as cables, PCBs, you might see, with respect to 0 dB, you might see a PCB over a span of 20 gigahertz. Mode conversion maybe look like this. In cable, you can see some really funky effects. You see some harmonic nature, some dips, some nulls. Obviously, this wouldn't go past 0 dBm or 0 dB. But really, at the end of the day, we care what is the magnitude of SCD21. This is really what we care about. In high-speed measurement, channel design, we really need to understand what causes this magnitude to get higher. And fortunately, it's this simple formula right here that can really give us the answer that we're looking for. So we're going to bring this down here, and we're going to continue further with this investigation. So because there is a real part A and a complex part B, if you sit down and derive the formula, you can say that the magnitude of SCD21 as a function of frequency, which I will not be putting the variable argument further in the equations. I'm going to basically assume that you know that this is at each frequency point. The magnitude of SCD21 is therefore equal to the square root of A minus B cosine theta AB squared plus B sine theta AB squared. This is the general formula with our differential distinguished notation. Now let's pretend to make ourselves, or to make this problem even more simple, let's assume that we really only have 2 factors that we care about. And this is really honestly what you care about in real practical applications. you care about the magnitude or the phase deviation, AB, so that's 1. And then the other thing is that you care about the ratio of the levels A and B. And you'll see why that is in a moment. We'll call this D. So that is, again, the ratio A to B. And therefore, from there, we can say that B is equal to A divided by D. Now this is where it gets juicy. Let's bring our formula here and simplify it further. Now the magnitude of SCD21 is equal to A minus A divided by B cosine A B squared plus A divided by D sine theta A B squared. Great. And we're going to do this step by step. So let's simplify this further. We can now pull out the A from this argument here and say that this is now square root of A 1 minus cosine theta AB divided by D. Draw that a little bit better. Divided by D. All these squared plus A squared sine theta B divided by D squared. And finally, we can pull out A again from this entire term. Square root A squared 1 minus cosine theta A B divided by D squared plus sine theta A B divided by D squared. And finally, we reach our general equation. I'm going to write it in like red, that the magnitude of SCD21 at a particular frequency point equals A times the square root of 1 minus cosine theta AB divided by D, squared plus sine theta AB divided by D squared. Whew. I know that was a lot, but this is it. This is our general formula. Now you'll notice something very interesting here. We brought up the fact that our SCD21 magnitude is definitely a function of the phase variation between A and B being the SSD41 and SSD21, and also their magnitude differences. But we also left out one variable, and that is the fact that SCD21, the magnitude of it, is directly proportional to A, which is proportional to loss. This is really important. In IEEE 802.3bj, there is what is called an informative, which means it's just a design guideline, spec called SCD21 minus SDD21. When I was first introduced to this, I wasn't exactly sure why this was happening. It didn't really make any sense. No one really knew what was going on, and so I had to think about this. And once you derive the equation, it starts to make more sense. Mode conversion is directly proportional to loss. So the loss is almost tricking you into thinking that your interconnect has this much mode conversion. So what I mean by that, let's say we're measuring a cable assembly. It's a 5-meter cable. Our mode conversion may look something like this. You'll notice it goes down as we go to higher and higher frequencies. That's because there's more and more and more loss. So let's say you're at 10 gigahertz and your level is let's say minus 60 dB. You think, oh boy, that's amazing. Like I have really low mode conversion and this is great. I don't know what I'm trying to draw here. It's a little stick figure. I was trying to make him go. Yeah, there we go. So anyway, you get a profile like this. And so as you learn more and more about mode conversion, you can use mode conversion as a way to debug where you are losing differential signal loss from. And if you're just using plain SCD21, it's really hard to debug it. But if you take into account that your mode conversion, that the loss has a factor into it, and you divide or subtract in a dB environment, aka subtract SCD21, which by the way represents the loss of your channel in the best way possible, considering that your reflections are low and a lot of other things are taken care of, your mode conversion can now look more uniform, which is a great thing. So that is why in the IEEE spec, they're using this as an informative spec. They're not just focusing on SCD21, they're focusing on what I like to call loss independent mode conversion. Okay, so now we know why that's taken into account. So let's go back. We can now say that our SCD21, our loss independent mode conversion, that the absolute amplitude of that is basically equal to the square root of 1 minus cosine theta AB divided by D plus sine theta AB plus D, all these squared and this squared. Okay, great. Now let's assume a situation. Let's assume that we have a PCB board trace, and let me redraw that in green since most dielectric is shown on the screen. Let's say we have a PCB board trace, and let's say we have a differential trace, and let's say it's 1 foot. 1 foot long. Let's say that the copper traces have the exact same geometry, the exact same plating, they're identical. The only difference in this entire structure is the fact that, let's say that region 1 here has an epsilon, let's say of 3.8, and let's say that region 2 has an epsilon of, let's just 4.1, let's say. So let's assume for a second that D is practically 1. Remember, D was defined as A divided by B. So let's just assume that their losses are very, very similar. But because they have different dielectric constants, or local dielectric constants, the speed of the waves in the particular regions 1 and 2 is going to be slightly different than the other, and because of that there's going to be a phase difference. So in this situation, we're going to say that 1, D is basically 1, and 2, that theta AB is not equal to 0. So what does that make our equation now? SCD21 loss independent mode conversion is equal to the square root of 1 minus cosine theta AB squared plus sine theta AB divided by D. Oop, sorry, I forgot we're not including D. B squared. Well, sure enough, it turns out that if you take into account the factor of 2 division that we were talking about earlier, and we do some quick tricks that if we're just talking about phase difference, or if we want to think of this better, a time delay difference, between the two vectors, or the two waves, difference, then our magnitude of a SCD21 breaks down into a very, very, very simple formula. And that is that it is equal to the absolute value of sine of theta AB divided by 2. This right here is an amazing equation because it basically allows you to understand and allows you to understand mode conversion and reading mode conversion plots and basically guessing whenever you look at a mode conversion plot what is the culprit for high values. So we can see that all these things that we talked about in a particular situation where the losses are the exact same, we take out the channel loss factor, or the loss is very, very low, therefore A is equal to 1, we wind up with this beautiful equation right here. So in high-speed systems, right now our formula is in radians, and when we're doing measurements and signal integrity analysis, we don't want to be using radians. We mostly want to be using time delay values, skew values, which skew is nothing more than the time delay difference between the differential components, let's say SSD21 and SSD41. Yes, I think that's correct. So we really want to take this formula and we want to convert it from radians to something a little bit more useful. So assuming a lossless situation, we can say that the magnitude of SCD21 on a dB scale is equal to 20 times the log 10 value, absolute value of sine, pi times the skew or time delay difference between these two guys right here, picoseconds, times our frequency in gigahertz divided by 1000. This right here. This is the useful equation. So when you're in your lab and you're taking something such as a PCB trace, like the one we have up here, and you're measuring, let's say, skew. And let's say that this is simple skew. So you have one waveform like this, and then you have the counterpart like this, or if you want to draw a little more technically like this, and they have some skew, typically in picoseconds between each other. You can use this formula to estimate your SCD21 profile. And there are much better formulas, but this is just a really quick rule of thumb. Where can you expect there to be a maximum? So let's say that we have a skew value here. Let's say our skew value is, let's say, 100 picoseconds. Okay, we can use our formula and we can plot SCD21 on a dB scale as follows. Let's say that this is 0, 5, 10, 15, 20 gigahertz. In a lossless situation, we can expect our mode conversion plot to have nulls here, here, highs here, here, here. So at the end of the day, it will look like this. This is really important because let's say you're operating at a speed of 10 gigabits per second and you have a skew value of 100 picoseconds. That is going to cause your mode conversion to be maximized at 5 gigahertz, which, if you don't know, is the Nyquist of 10 gigabits per second. What does this translate to? Your design will not work. or it's fairly unlikely that it's going to work. So this is where these formulas and these decomposition techniques can be really useful. They give us really great rules of thumbs, and I know this was kind of a lengthy and long and boring explanation, but this is what I want you to take away from it. I want you to take away the fact that you can measure the skew of a channel, and just by knowing the skew, you can have a really good estimation as to what your mode conversion plots are going to look like. Now, whenever you plot SCD21 in a lossy situation, you're not going to see the blue here. You're going to see maybe something more like this, but in the same fashion that we saw above. But you'll notice that the nulls here, let me highlight that, the nulls and the peaks and the areas of these guys aren't going to be changing very much. So that's the secret. I've gotten to the point where I can measure a differential channel on a VNA, and I can plot the SCD21, and if I get a mode conversion plot that looks like this, let's say it's a PCB trace, instead of going to my time domain instrument and measuring skew, I can go to this very first null point and determine my skew from that. So in a nutshell, I just wanted to share this information with you guys. And so I come up with a little quick formula or table right here that has your mode conversion at Nyquist and the quality. So depending on your data rate, a skew of 20% UI versus a skew 15% UI and 10% UI. At your Nyquist in this lossless ideal situation, you can expect your mode conversion values in the first case to be around 10 dB at the Nyquist, second case around 15 dB at your Nyquist, and in the third category around minus 20 to, let's say, minus 25 dB at your Nyquist. So if I could easily, I would say that this is okay, this is good, and the last one is great. So I would always shoot for skew values in your differential channels to be no more, if you can, to be more than 10% of your UI. And so that's about it. I just wanted to share this information with you guys. I know this was a very lengthy, long explanation. It may have been kind of boring, but thanks for staying around. And I hope you guys have a good one. Thank you.